Ah, yeah, sorry. Hopefully this is recording. I mean, volume-wise and all that kind of shit. Yeah, I'm using the other computer again. The one that was the better computer that's now working like the shitty computer. But anyway, computers, such a problem. Anyway, that's a whole nother reason for a room, I think. It's just to, complain about all the glitches. Anyway, especially when you want to cling to the old, the old. I don't even know. It's just kind of funny to say. I'm a fan of XP. I just don't like. I don't like change. You know, well, I want my old software to work. And it's just irritating to have to give up on that idea. It's not really software. It's just one editing program for videos. I just don't want to learn how to use another one. I mean, you can't even find one that's any good. You can't buy a cheap, good video editor. Anyway, they all suck. So what do I want to do here? Oh yeah, I want to go to the live room so I can read whatever cruddy chat there might be. And whatnot. So that worked. Okay, so now I can make this window smaller. And there we go. Okay, so now I can see the crappy chat and such. All right. So a couple of subjects, I think. I always periodically rewatch Feynman videos. The Auckland, New Zealand thing, and the other public lecture series he did, back in the '60s. So it's like the '60s and the '80s, or the early '70s and the '80s. I think it must have been the '60s because it was pretty bad quality, the old one. Anyway, really had to be, yeah. Anyway, it's quite dorkier. It is kind of funny how he kind of did undorky himself quite a bit, style-wise. Became modern. And the other thing was that Ken guy again, right? So he's getting less and less. The things he's doing now are just so silly. So he does a video about with a quartz crystal and his magnet, and he talks about how he can feel the pull on the quartz crystal from the magnet, and you're just like, I mean, how hard is it to tie a piece of string to a quartz crystal and dangle it, and then try to move it with a magnet, try to spin it, try to do something? I mean, it would be just silly to say, I can feel it. I mean, it's just such a silly. He's making this bold claim, and to do it with such a silly experiment, like I feel it. I mean, it's just so bad. So actually, I lost a lot of. I thought he was kind of intelligent, but you have to be really stupid to think you can pull that kind of crap. I mean, not to even have enough concern about your experiment having some integrity to do the obvious and move the crystal by moving the magnet around it. But anyway, it's terrible. Horrible, awful video. And I don't know if he'll ever address the arguments about his claim that he's bending light with magnetism because of the ferrofluid thing, the ferrocell thingy, whatever it's called. Yeah, I mean, it's just it's just terrible. And people really do support him in this, because it's all the Tesla shit. He says all these words that nobody understands, and they think that's physics. a loss of inertia. I still don't know what the fuck that means. Magnetism is a loss of inertia. So anyway, so I did get to the the Feynman video. Maybe I'll post a link in the description later. It's the whole thing in one video, so it's like 6 hours or whatever. And, on the subject of light. And he was just getting to the part where he was talking about the refractive index. And the, he does call light a corpuscle, which, I do like. He does say it's a particle pretty explicitly, which I do like. But later he'll be, playing his wave mechanic bullshit. But I mean, he does say it's a, he does say it's a particle. I mean, he says it pretty overtly. So I'm surprised Feynman, Piro is such a fan of Feynman, because Feynman was pretty, direct in that assertion. So anyway, at least the wholeness, it doesn't have any other wave property. So, but it's all this probabilistic stuff. So, and Feynman basically claims that the probability is somehow built into reality, and it's not a consequence of a circumstance that exists. And he always does this, not always, but in his older lecture series, the older one, he debunks Lesage gravity, with a raindrop analogy, a pretty poor way to explain something that's physics, very small things. Start talking about raindrops, that's not exactly ultra mundane particle, as Lesage would describe it. But anyway, rain's not exactly ultra mundane. Anyway, but it's just this casual kind of dismissal. So he does it again in analyzing possible explanations for the fact that you do have a probabilistic likelihood of reflection off of surfaces by light. So the percentage of the light will reflect. And obviously you're saying it's probabilistic which photons actually get reflected. But we could argue that the probability is structural. It's not probability like, they decide to be something. They're being forced to be something. So the probability is in the mechanism. So anyway, he uses the example that Newton had talked about, where maybe the glass has a defect in it that makes it 4% or 2% reflective. So when the light hits one of those freckles in the glass, it reflects, and when it doesn't hit a freckle, it doesn't reflect. And then Newton's argument was, Feynman's argument about Newton's argument was that you can polish glass, and therefore there couldn't be a freckle thing because you'd polish the freckles off. And that's kind of a silly explanation, and it doesn't deal with it again on this, smaller level. When you're talking about the reflection of a photon off of glass, you're talking about something interacting with the atoms of the material. That's where the reflection happens. Glass isn't glass at the subatomic level, right? I mean, at the atomic level, it's not glass, it's atoms. And what makes it glass is how the atoms are arranged. But the atoms themselves are not like special glass atoms. The atoms are elemental atoms combined in a compound. And the elemental atoms will have a facade, a surface that may be different than the substance, technically. So you could argue. So the real point is that as you change the thickness of the glass, the reflective index changes. So depending on, so in this sine wave kind of way, except it's not a pure sine wave, because I think it has to be pretty peaked. I mean, it's a sine wave in that it's proportional, but I mean, I think it's a peaked wave because it goes from 0 to 16% when it should be 4%. I think it's 4%. I think it's the correct number. So if I made a mistake in the lecture, and so it confuses things a little. So it's the square of the number. So it's not like it doubles to 8. So it doesn't go like, so the average would be 4. And what's really happening on the subatomic level is that average is just an average over all thicknesses and all ranges. But the fact is you can change that for average to a specific number of 0 or 16%. So you can make glass highly reflective, 16% of the light, or not at all reflective, theoretically 0 reflectivity, based on how thick the glass is. And that it would go 0, 16, 0, 16, 0, 16, 0, 16, 0, 16. So that ratio would just keep cycling through the thicknesses. So you could go 10 feet thick, and you could still polish the glass into this cycle of 0 to 16. So it's a recurring pattern. So lots of thicknesses will create 0, lots of thicknesses will create 16, but they're very specific. And apparently they use this technology on, submarine windows. Apparently use this fact to create less reflectivity. So when you look through the window, the light doesn't reflect back at you. Because it's dark out there in the ocean. So any reflection is going to be distracting to your purpose of seeing the Squidwards and whatnot. So it just seems like Feynman, okay, so he dismisses it based on some idea of spots on the surface of the glass, and doesn't go any deeper than that. It doesn't really look at the atoms and say, well, what really happens to glass as you make it thicker? And I think, I've made the argument that clearly what happens as it gets thicker, they can line up more completely or less completely. They can fit in the space. The atoms can be whole atoms that fit or half atoms. It's like packing a box for mailing. And you can have a box that's a half too big or a box that's a millimeter too small. And then sometimes you can take the item and just bend it a little bit and it'll fit in the box. And sometimes the straight line will just go a little crookedy to fit in the space. And that little crookedness is a difference in the shape of the molecules in the glass. So clearly, people have even argued that glass is technically a liquid. So clearly you could understand that the molecules, as you polish the glass, would certainly arrange to the thickness of the glass, in the sense that the atoms want to line up geometrically straight. That's what makes glass transparent, is the idea that it wants to make straight lines in its matrix. Probably a better word for that. It's another word for a pattern in a substance. Well, matrix is good enough, I guess. There's a better word though. But anyway, so it's just the idea that there's a confined space, and at one point you're going to be a half an atom too much space, or too little space, however you want to look at it, right? The space is just a half an atom too small. So somewhere that half an atom something has to give, something has to be changed in its position. And it's the changing of that position from all the atoms fitting perfectly to all the atoms being bent on the surface that is causing, in my opinion, the recycling of the pattern. The pattern is a consequence, the reflectivity is a consequence of how perfect the glass structure is. And so it's perfect, let's say when you have zero reflectivity, that's when all the atoms are just perfectly lined up. And when you have the 16 is when they're the most irregular on the surface. And so there's the most likelihood of the photon being reflected angularly, because the electrons aren't in the same, they don't have as consistent a position on the surface. But I think that's it's a perfectly rational explanation for why the pattern exists, instead of this projection of some magical, it's just the way it is probability thing. Like, and Feynman even does this in a lecture where he starts arguing about how does the bottom surface know how reflective the top surface should be. And, it's sort of an argument where you're saying, yeah, well, that's only true if you think the atoms at the surface, the top surface, have nothing to do with the atoms at the bottom surface. And I think we know the atoms, anything that happens to an atom one place is going to happen to an atom every place, because the atoms are all electromagnetically tied to each other. That's how they're glued together. There's a field of electromagnetism. So you can't move one atom, theoretically, without moving them all in any substance. Yeah. It's just a transference of the magnetic field. If we just pop a bunch of magnets on a piece of, I've done this with these little magnets. I have a bunch of these little tiny ones. These are little ones, all connected to each other. You put them on a piece of paper, and you can just all arrange them all just right, so they're balanced. And all I have to do is hit one of them, and like dominoes, they all move. They'll all cascade into each other. This is sort of an interesting magnet. So there's two, a solid magnet here, and then the little ones here, and you get this idea where they're repelling each other at the top, which is quite interesting because they're all lining up, of course. So, but there's no repulsion that's nearly as strong at the bottom, because you can push them right together, and it's only at the top it's realized. It's sort of interesting, but it is quite a strong effect. Anyway, so where was I? Yeah, so it's just another example where physics just keeps doing this kind of stuff. It clings to some. It's given it's a problem is presented, and it seems to just want to go for the improbable or the fancier answer rather than the simple answer, and it keeps just mocking the simple answer, as if you're a fool to have some expectation that it would be simple, and that you really should look for that simplicity in the mechanical structure, the checkerboard. Something, very few properties, very few functions. That's how logically you would deduce the elements are. The elements don't get more complicated. They get less complicated, less sophisticated, less, fewer properties, not more properties. So yes, the answer should be, the solution should be a simple answer, not a complex answer, like God plays dice with the universe, as Einstein would say. But Einstein was kind of silly in the sense that he made that statement. And yes, and yet he talked about how nothing makes something move, and then when the something moves, it tells the nothing to be something. What? Yeah, it's pretty circular, incredibly circular. not an answer to the question. It's really not a mechanism. I mean, bent space isn't a mechanism. There's no way to see it as anything but a pulling engine, in the same sense that you're still not told how it pulls. And I would obviously argue it's a pushing force. Hi, Gary Doll. I can live without that. Wobble. The repulsion is not stronger at the top. It's the moment arm that's longer, thus larger torque. Well, I mean, they're just magnets, right? So, I mean, what's really, I think, happening, I mean, I don't want to get to a whole bunch of stuff on this, but is that these magnets, when they combine, is sort of like what the atoms are doing, you know, in the sense that they combine to become, it's like this row of magnets becomes one magnet. And then when this is on another magnet, this whole thing becomes a magnet. So it's like having a magnet that I saw, you know, into flexible pieces. So in a sense, this bottom is part of this big magnet now, and the top is still, you know, kind of a, it's got a little more freedom because it's more these magnets than it is this magnet. But it's like trying to be one magnet. It's always, that's what magnets are always trying to be, is one magnet. Magnetism just tends to do that. They all line up and it just makes a bigger magnet. Right? I think that's right. So anyway, yeah, I got these really powerful ones over here I've been playing with. These are nasty strong. I mean, just vicious animals. But I was doing this thing with this ball, and it sticks to one side. Oh, see, it's only sticking to the one side. Okay, oh, there it goes. Okay. So, you know, I was just trying to figure out what causes it to choose what side it sticks to. So I found that a little bit interesting. But anyway, but these are, yeah, they're just brutally strong. I mean, they'll, you know, it's almost like they hurt if they, on your fingers, that give you a good pinch. Anyway, but yeah, so, where was I? Yeah, well, we can talk magnetism, but yeah, it's the light thing I was on. And the reflective index. But so I'm just saying that, so, you know, it's just every time there's a simple solution, like I said, physics seems to jump for some complex solution. And or some solution that requires a multiverse or some dark thing or some undetectable thing or some invisible thing. Like I said, space-time is just not it's not a tangible dimension. And so it doesn't, you know, we can't see how it's moving planets. We can't see how it makes that happen, which is a cheat. I mean to say that space-time is making this battery do this, it just, you see how that's such an incomplete answer? I mean, how exactly does the space-time make that happen? It's just such an incomplete answer, and completely not applicable to this thing where the magnets are doing the same thing. They're just doing it in a different way, but it's the same repulsion and attraction. Well, there's no repulsion with gravity, though. But it's close enough to similar, and the whole fact that they all move the speed of light, and it just seems like, yeah, it's just so. Where was the point where it really got interesting? But some guy kind of just admitted it, in the sense that, yeah, the Maxwell equations. So what they did was they used this as validation So when they found out that, that light travels the same speed as magnetism, they decided to turn light into a wave because the wave equations were applicable, I think. Or maybe it was electricity, charge. I'm trying to think of which one it was. Well, anyway, but it's just kind of funny that they could have gone the other way. They could have said, let's make the force a photonic force, the electricity or the magnetism. So they had this choice, a simple little choice. And it's just like that they decided to make light into what they understood the waviness of, say, an electron, the complexity of an electron. Maybe that's a way to say it. Because that's where this all breaks down. I mean, see, that's something like Feynman was always talking about, is that it's only about two things. I mean, photons and electrons. I mean, that's where most of these interactions are taking place. But they're not the same thing. They're fundamentally different. They're just talked about as if they're the same kind of particle, or they're brother and sister. And they're fundamentally different. They're as different as a cell, on my body, and, a whole system. It tries to be one magnet, but because the collection of little magnets gives it extra degree of freedom, the moments become more realized. Well, I don't know what that means, but I think that's what I just said. But fine. My point is that the reason why it's not as impatient down here is because, like I said, it's more trying to be this magnet, and up here it's still these two magnets. Yeah. But magnetism is really quite interesting. But it doesn't bend light, and it's not going to. I mean, I never did any experiments with quartz crystal and magnetism, and I certainly did plenty of experiments with electricity. But yeah, but I've never. I worked in a machine shop, and we made guide control machines, for printing and cutting and whatever. So we used LEDs and other light sources to be able to find holes in plastic materials and all this kind of stuff. But anyway, yeah, magnetism and quartz crystal was never. I don't remember ever having any magnetic effects on quartz crystal. I mean, I remember being able to create electricity or bend a crystal by applying magnetism. You had to always apply a mechanical compression of the crystal, from my recollection. I mean, because we did some work with ultrasound, ultrasonic transducers, and I think they use quartz crystals to create the sound, to vibrate the air, and the sufficient high frequency. And it'd be nice if you could just do that with a magnet, right? Like a speaker or something. But anyway, so I mean, it's just such a bullshit thing, right? I mean, I'm just saying, if you're saying that there's quartz crystals have a magnetic component, then you can just demonstrate by suspending a crystal from a thread and then moving it with a magnet without touching. It's so obvious. So anyway, so really bad on Ken. So any Ken supporters, I mean, I wish I could get to them somehow. I mean, there's a point where you have to call him on some of these shoddy experiments he does. Never before seen kind of experiments. First time ever seen. I've proven, I mean, all these big, bold statements. but nothing to back it up. So I don't know who that was that popped in the room, but I really wasn't in the mood for shitty visitors anyway. So anyway, the link is in the description if somebody's in the mood. But only 5 viewers. It's not really reaching a useful audience here, which is irritating. I mean, eventually, maybe it'll be. Oh, not Piero. Oh,
Hey.
fuck. Boo.
Why do I not have a picture? Google's all fucked up all of my accounts and done weird shit. Can you hear me? Oh, you can't hear me?
Yes.
Here, let me check my audio.
Yeah, make it louder. Why don't you make it a little bit louder and more annoying?
So I had to reboot my computer, but I was listening when you started. I had it open and it started. So I heard a little bit.
Yeah, well, I just don't know if there's any fruit to be born in a conversation with you because you're just.
Well, why do you think why are you surprised I'm such a big Feynman fan?
Well, just because Feynman in the lectures he did in New Zealand, right? He's pushing pretty hard.
Which ones are those? Okay, I'll look it up. I'll remember from the picture. Go ahead.
Auckland, but well, there's only 2 lectures. There's
they're the Oxford ones, which are those '60s ones.
Yeah, right. Then
he has the ones he did for the hippie kind of.
Right. That's the
and there's an interesting interview about how flaky he thought those people were in the end. It was kind of pointless, but they're good lectures since they were filmed. But the audience was a bunch of morons about it.
Yeah, I know, but they really weren't on the heart of it.
Which one is Auckland's the third one?
Those later lectures were on things like nanotechnology and that kind of stuff, so it really wasn't, you know what I mean? It's physics, but it's not physics, if you get my drift. It's a little bit Hawking-esque, it's a little bit too tied.
Well, he was getting older, and he definitely was trying to make it more understandable, but he was always like that, trying to make diagrams and things to simplify it, but he did try to simplify it. Also, the BBC interview is another example where he's a little bit hokey compared to, in a way, the best Feynman is, except for he learned a lot, so I like listening to him later, but that 1960 Oxford lecture series is him, right? He's funny and everything and entertaining, but he's kind of right to the point of things. None of the hokey part, but both guys get hokey. I
guess I would argue, though, that there was a lot of errors in that lecture because that's where he did the 2 slit and he, misdescribed the.
Well, I'm just saying the Auckland one, right? Yeah, no, those were good. Which anyway?
Well, I'm just saying there's if you it's 6 hours worth, but I'm just saying in the first lecture he pushes pretty hard this whole idea that Newton called it a corpuscle, and it's a corpuscle, it's a particle,
right?
So it's not a wave, and he pointed out how it's, it doesn't have any wave characteristics and that there's no partial photon. There's a complete photon and that's it. And then he went on to talk about probability and do his clock thing and explain that, okay, so and his point was you don't think.
The clock idea is.
Well, I know the clock, but the clock idea is just a gimmick. We know that.
Well, but wait, it's a different.
The clock is he's just duplicating a repeating pattern, a sine wave, a repeating pattern.
Exactly.
Right. So
that replaces the wave idea in your head.
Well, I mean, but it's a gimmick that disguises what's.
It's not a gimmick.
It's a gimmick.
Everything's a gimmick.
Well, I'm just saying it doesn't get to the real point. Okay, it's the problem.
Well, what it does though is you should like it. Maybe you are saying you do because you don't have to picture in your head a wave. It really is. The math will remain the same with any cyclic metaphor you can come up with. Fish in a circle, for example. Fish swimming in a circle.
You're just not listening, okay? So this.
Yep. No. You're not listening because I haven't even made any assertions.
Sentence, and you're interrupting. I'm just saying I don't think it gets to the real point of what's happening. The thickness of the glass is changing the reflectivity of the glass. That's what he's describing. So he's using Newton's rings and the reflectivity of glass as the example to explain this probability thing, and then he explains the clock thing. So I'm just saying the clock is a rather poor representation of the fact that there's a proportional relationship between reflectivity and thickness of the glass, which is obviously why lenses work.
My question is, why would you think I wouldn't be a Feynman fan because of this particle idea?
Because he's not a wave guy, he's a probability guy.
It doesn't really matter to me if the thing could be thought of as a wave or a little spinning clock or anything like that. To me, it's all about getting models that fit the current evidence, right? And of course, you're going to change and have available a lot of different models.
I'm saying the model should be explanatory and it should be simpler, not more complicated.
Well, sometimes the model is so good you discover a physical thing that isn't part of the model, but really is out there, like a photon. At first, where those look like, maybe it's just part of the model, and then it's like, we could tell sometimes when something is real. Well, we always should be able to tell whether it's physical in that sense or just a part of the model eventually.
What I was pointing out, though, is that you can see a correlation in Feynman's attitude between the two lectures. In the 1950 lecture, he dismisses Lesage gravity by comparing it to raindrops. Kind of a ludicrous comparison, right? I mean, a gravity that's, even described 300 years ago by the author as ultra-mundane particles. Obviously, raindrops aren't ultra-mundane. But anyway, so it doesn't even do anything like fairly approximate real physics. And again, when we go to the light experiments so now in the 1980 lecture, he does the same thing, is he's saying, okay, here we have this phenomenon where glass reflects. And somehow, well, how does the glass know? How does the photon know it should be reflected or not reflected? And so he's turned it into a phenomenon that's happening outside of the glass, and it's somehow the photons are deciding. And so he used the example of spots on the surface of the glass, like Newton was speculating that it could be spots on the glass. But then he said, okay, well, I can polish the glass, so there can't be any spots because I can polish it. But I mean, the whole point was it was through his polishing of glass that he realized that the thicker and thinness of the glass is what decided the reflectivity. But I'm just saying, so Feynman's argument was, again, this simplistic notion that never got to the subatomic level, where we know on the subatomic level, the light's interacting with the electrons in the glass. And we certainly know that in all physical substances, if I change one atom, I change all the atoms.
But it's not only interacting with those electrons.
But the point is there could be a simple explanation.
Well, for example, I wanted to say one explanation of something that you said earlier.
Well, let me just do this simple example. So let's say we have a little Pac-Man or a little smiley face, and it's a 3 inches round ball, right? And I fill a box with them, right? And there's a point where you could say, okay, if I make the box an inch higher, then all the balls can bounce around because there's more room in the box, right? But if I make the box exactly the same height as the diameter of the balls, then the balls don't move at all.
Right.
So I'm saying an explanation like that can explain why surfaces have a reflective index, is because the atoms have to actually fit in the box.
Well, it works with waves as well. They say the wavelength has to fit the box for it to,
well, again,
to add up and whatnot.
Another 20 seconds to the point I was making is that it's not a coincidence that this cycling happens with a very minute removal of a surface size. Okay, so this cycle happens over a very tiny amounts of glass being removed. So it is kind of the size of the atom is making the difference, kind of a thing. You're talking
Which atom?
The atoms inside of the glass.
Mm-hmm.
So we're talking about something where all you're doing really is taking a molecule of glass, and because the
glass is, right?
Well, yeah, but the fact that the glass molecules can't fit in the box the container they're in, is what's causing the reflective index to change, because the surface molecules are being caused to be bent because they can't fit in the size of the surface. it's changing the angle of the electrons.
Yeah, the geometry.
Right, because of the
That's
size.
fine. I mean, I just think the geometry is different than what you're saying. But yeah, it is the same effect. I mean, basically.
Well, I'm just saying that that mechanical explanation, okay,
It has to be something like that.
I'm just saying it provides a perfectly reasonable mechanical explanation. So why we don't
No.
need to think of it as a probability that exists in a vacuum. It's a probability that exists in a physical reality.
No, but here's why.
With what Feynman was saying, he was saying quite explicitly that the probability is in fact the reality, and that he wasn't saying it was a physically caused phenomenon. And that's the part I just saying, I think that was a huge
Okay, right. But
mistake.
can I just go back to what you were just asking? Okay, so the thing about the thickness of the glass and the reflectivity, okay, it has to have to do with the geometry and this fitting together thing, whether it's waves, particles, whatever, because of the fact that it doesn't just get bigger or less as you make the thickness of the glass different. It goes up and down again, and that's because sometimes it fits and sometimes it doesn't fit quite right, because it's not just when you have a box that's the size of the balls. If it's a little bit bigger than the balls, they'll vibrate differently, and they can also all get in sync with each other differently depending on the thickness. So, but the reason it seems like waves is to people, it has to be a frequency phenomena, like particles have frequencies in some sense, is because the reflectivity of light of different frequencies, of different wavelengths, of different colors, you know, it reflects different with these thicknesses of the glass. The thing about glass is it's not really that great a thing. So like glass is quartz, strings of tiny quartz crystals, basically threads of quartz crystals. So it's like threads. It's funny why that it's so transparent, but real crystals are better for putting light through than glass.
Well, I know, but
Because they're totally organized, you know what I mean? No random thread shapes.
Right. No, but part of my argument would be is that that's what makes glass kind of very interesting, is that you have a 40% reduction in the speed of light transmission through it. So quite obviously, each photon is taking an eccentric path through the glass. I mean, it's
well, you think it's following these threads somehow, and it's still coming out the other side.
It's obviously not driving an interstate highway. My point is, it's driving a really windy road to get to the other side. Okay, so it's not it's taking a big spiral, or it's, you know, it's doing some fiber optic type thing. You know what I'm saying? Where it's ricochet rabbiting through the glass and still ending up with the right angle of exit. You know, so it's leaving at the right angle at the other side of the glass, which is the amazing part.
Right. Okay. So this quartz crystal, it is pretty amazing, and I guess the quartz crystal threads in there can get really long and be interesting, but let's say that it is just an actual quartz crystal, a thin quartz crystal. The thing is, when a photon goes in there, all the photon is the disturbance of those electrons. The amazing part is that it can fly along where there aren't any electrons, but maybe that's because electrons popping in and out of existence, or who knows why.
No.
Wait, no, let me finish. Can I just finish? No, you want it. Let me just finish. I will keep it quick.
Do multi-dimensional.
So so I'm saying when the photon hits the crystal, all the electrons that in the quartz crystal are shared, because it's really just a giant molecule with tons and tons of atoms in it, and all the electrons in there wave like the water wave, you know, waves when water wave goes through, and that spits an a photon out the other side. So if you have all these little rivulets of winding paths of threads, quartz threads that aren't quite crystallized all together, but they're crystals in themselves all lying together, making a plane of regular decent glass, you know, obviously the way the electrons wiggle, the electrons in there, instead of just wiggling regular like in a pool, it's as if you had a bunch of, you know, divisions in the pool. So little waves will run along those divisions. But on the other side of the pool, you're going to get a photon, this particle, spit out anyway. And I maintain what's weird is, I had to use a particle and wave, you know, to describe that. But that's what it looks like.
Well, I think the better example is that you can take fiber optics and you can just basically melt them. So you can take a bunch of fiber optic fibers and melt them, and you end up creating a kind of glass-like substance. And that light goes in one side, it comes out the other side, and
well, I'm just saying that's what glass really is.
Separated but not separated. So I know, but when you say wave, you're implying like, okay, the vibration is evenly distributed. And no, the vibration is very unevenly distributed. What I would argue is that it goes down certain electrons, because of the rigidity of the crystalline structure. So they're almost like little fiber optic channels in the glass. So the glass wants to create a nice, a very geometric pattern of very straight lines. And so in a sense, the glass is traveling that a vibration in the electrons. I'm agreeing with you. That's what it's causing. Okay, the photon hits an electron at the top. That electron hits the one next to it. That one hits the one next to it. That one hits the one next to it. And the vibration goes all the way down the bottom. And then the last electron can't leave, but it can shoot out the photon.
Right. And when you say bumps, since they're all negative, they push each other normally. It's like very.
Well, I'm just saying the force between them exists, and so essentially there's already gravitons between them. I would argue. Okay, so the force that's making them repulsive is the fact that the gravity is making them repulsive, magnetized gravity. So the photon's already going that way. It's just that this particular frequency is maintained in the vibration of the electron. So you're basically, that's all a photon is a frequency. What makes what makes one end of the spectrum different from the other end of the spectrum is just frequency, not the ton itself. The tons are exactly the same. It's only the frequency of them that changes.
As a side note, how this has always come up where they say they have these crystals they could put in front of a slit and tell if a photon goes through or not without stopping the photon, which you don't believe, right? This is how they say it works. Is since the photon goes in there and wiggles the electrons in that crystal, they have a little magnets to detect. Wait, let me just finish. Detect it on. Can I just finish? Detect it on the side, and however much energy they detect, they put back into the system so that all so the wave still collapses. And now you're right. It might actually be killing one photon and creating another. But a photon does come out the other side. So you could see how the math of that. They might be interpreting it wrong. Actually, I'm not sure about that. I think it is actually regenerated. That's why it'll kill that pattern, because it isn't the same photon is what is almost proved there. But anyway, you can see how it's the same thing. It's like a splash pool or a wave pool of electrons. It's definitely what's going on when the photons go through stuff. So when they go through empty space, there's still electrons. Just because it's really thin, there's still electrons around. Even in empty space, maybe even if it was a light year away, but it would never be that far away.
If they hit those, they'll be diffracted. So I'm just saying electrons are very dangerous for a photon to hit. So I don't think they can survive interaction with an electron and end up coming out the same way. That's improbable. That requires structure.
Well, they'll have to be
random electrons will scatter light. Okay, that's kind of like what the atmosphere does, right? It's a lot of ions and a lot of kind of broken atomic structure, muons, that kind of stuff. They're the ones that fuck up light. You know what I mean? They're the things that send light going the wrong way. Cause a lot of diffraction.
Yeah.
But back to your crystal point, the point I wanted to make is the time sensitivity. So my argument to you is what they're doing is, yes, for the portion of time, right? The photon goes in, and when the photon leaves, it'll be a while. Right? So let's just say it's slowed down in the sense that the electrons do some moving with the momentum of that photon for a while, and then the photon's released. You know what I'm saying? So you get less movement because the electrons are much bigger, and the tiny amount of impact of one photon divided by the size of the electron is kind of a small number. But I'm just saying there's a lot of that's really what's happening. You always have to remember the time-sensitive part of this, that a photon is known by the speed of light. And whenever it doesn't move the speed of light, it pretty much means it's moving electrons. So as soon as you slow it down any, that's when, so that I would bet $1 million that your crystal has a time delay. And the time delay would be evidence that the photon isn't the original photon.
Well, here's the thing about whether things slow down or not. Is you know, water waves, the speed is dependent on the depth of the water, right? So if a water wave in a deep water comes along and hits a shallow area, it'll change speed. I guess it probably speeds up. And then on the other side, but even if it's the other way around, if the water's deep again, it'll go back to the deep speed. So did it really speed up or slow down? No, it went its speed,
but
and it was warped by interference of something else that interfered with its natural waving. Wait. Let me finish it this way. It went into a box where it didn't have room to fully, you know, speed along. Basically,
I know. We always have to do this wave thing, and
potential. Well, I believe it is.
If we're going to do it with this example, this is all I would say to you: is that a better example would be, is that lots of waves can hit a boat, but the boat doesn't end up going as fast as the waves because the boat's bigger. So when a photon hits an electron, the electron doesn't move as fast as the photon. It moves a lot slower than the photon, but it moves, and that's the important part.
But I just...
And it will stop moving as soon as that boat releases the photon. So think of it that way. Think of it as a photon goes in like a wave, you're saying, pushing a big giant boat. The boat gains a little bit of momentum, okay? But as soon as the boat fires the cannon, you know, off the front of the boat, you know, and shoots the photon, it stops moving.
Right.
Okay, so that's the equal but opposite reaction. So it gave back the force it consumed. It gave back its acceleration. So that's what's happening in, like, say, for example, glass, is the photon is being converted into electrons moving. The electrons move a lot slower than photons, and then the photon is released at the end because they have to give back the energy.
Yeah, let's say you had a big a wall in the water just on hinges, or, you know, a float or whatever, and the wave hits that. Obviously, it would move the barrier, and then the water on the other side would move. Now, in that case, did the wave travel through that barrier, or did the barrier get hit and then the barrier generated?
Can we have a premise of our argument or our conversation that will concede that an electron is maybe 1,000,000 times bigger than a photon? Or let's say a lot bigger. Can we at least concede that the electron is massive compared to a photon?
To the length of a photon?
No, to a photon's energy. The energy.
I believe a photon has a length.
Well, I know, but I can't do that.
Oh, the energy.
So we don't have a possible conversation. I'm talking about a photon's movement, its momentum. It has an energy quanta.
Right.
Okay.
Yeah.
And what I'm saying is an electron is huge by comparison. So
I believe that's correct.
It's like a little wave in the ocean hits a boat. It can't move the boat
the same
speed as the wave. So I'm not talking about styrofoam on a wave. That's not an electron. Electron is a battleship on a wave.
But you don't think if a photon hit or went by a proton instead of an electron that it would do anything?
Well, I mean, a proton is hugely massive, but I'm saying that a proton, I don't think it can get to a proton in the first place because I think the electrons are always going to consume it. But yeah, I'm sure that they could interact. I mean, gravitons are interacting with protons, but I don't think I think they go right through it. I don't think a proton can absorb a photon. A photon is a frequency. Again, let's get back to the frequency argument. It's force with a frequency. The force goes right through it if it doesn't have a frequency. You have to have
why does it have a frequency if it's a clock? If it has a built-in clock, then it makes sense it has a frequency.
Not a built-in clock. I mean, come on. I've already explained.
You got to listen, Gary.
I think photons are discrete objects. I think they're corpuscles separated by distance.
That's not going to answer my question. My question was, you say it has a frequency. The whole reason of talking about
photons.
Holy fucking shit. You say it has a frequency. Yeah. Yes. So Feynman And other people, the whole idea of saying, well, maybe it's a wave. It's because waves have frequency. Maybe it's a clock because clocks have frequency. So in what sense does it have a frequency since you don't like either of those?
Drops. I drill a hole in a bucket of water. The water drips out of the bucket. That's what I think photons are. Drops of fucking water. Corpuscles of water separated by distance. The less distance, the higher the frequency. The more distance, the bigger the frequency.
So a photon is like when you shoot those automatic BB guns and they shoot like 20 BBs down at the target. A photon is like a string of...
I'd rather keep them polarized, so I would like to just think of photons as frisbees. All right, and you can throw a frisbee two ways. You can throw it on its edge.
But not one frisbee.
Throw it flat. Yes, it's one frisbee. There's no such thing as a photon. Okay, Einstein was wrong to not figure out that there has to be two of them for there to be a ton, because electrons can't absorb them unless there's at least two of them. So yes, you have to have two of them, but there's two quantons in one photon, if I can say it that way. But there's no such thing as a photon in that sense. I'm saying they're tons separated by distance.
Okay, so there's two tons separated by a distance. The distance is the frequency?
Yes. I mean,
what keeps them together?
This is exactly, they're thrown that way. That's what the electron does that. The electron makes photons. That's the only way you get a photon. An electron had to make it, okay? And it throws it like a pitching machine, one right after the other.
And when it's captured, so it hits an electron and it can make the electron move, and then something else happens to the electron, it might throw it off.
I'll explain it to you, okay? So you understand.
How does it get stuck to the electron?
Let me explain it. Let me just explain it really briefly. A galaxy, you can sort of see galaxies have arms on both sides, right? So unlike a solar system, there's balance. There's mass on one side, there's equal mass on the opposite side, correct? All right, well, that's the kind of mechanism that an electron is. So it can only absorb a photon if it collects both the arms, the right arm and the left arm, or the up arm and the down arm. It has to collect both. So it has to, the photons have to come at a frequency where both of them will line up based on the spin of the electron. So as the electron spins, the first one comes in, and then at the right point, the second one comes in. Now the two are still balanced. Then the electron can absorb the photon. Otherwise, it will just release the extra photon and go about its business. It can't absorb it unless it's at the proper frequency. That's why electrons are frequency dependent. That's why some will absorb certain light and they won't absorb other light. Some will release one kind of light and they'll release other kind of light, because the energy level of the electron dictates what it can absorb and what it will emit.
So I don't know about that. But it sounds like it could be a very fun little video game, spinning around like that. But wait, you just made me think, if it's a frisbee, is it like, but the two tons aren't spinning around, are they?
No, the frisbee
just think about that.
Let me finish.
Okay, but think about that.
Look, I'm saying the universe is only made of this one thing, right? Tons moving the speed of light. They can come with no frequency, or they can come with frequency. They can have polarization. So when I'm using the frisbee thing, I'm just using the frisbee thing to analogize polarization, that they fly, they have a shape, and that shape can be transferred or it can be removed when they interact. So when they interact with an electron, they can have the shape of the frisbee change. The orientation of the frisbee is changed by the interaction. So I'm saying, but those are the only features in the universe. Everything is made of tons that have frequency or polarization. Magnetism and electricity is polarization, and light is frequency, and gravity is neither.
So these two tons that define the photon, they're flying in a straight line one after the other, or are they spinning?
Well, yeah, there are an array of them. So each ray is created by one electron. So one specific electron might produce 50 of them in a row, or it might produce 2. It just depends on how much energy it has to get rid of. But that would be a ray of a beam of light. So that's one individual ray. So if you have a white light coming at you, it's coming from different electrons that are producing different polarizations and different frequencies of light.
So when an electron's spinning,
but each ray came from the same electron and has the same polarization and the same frequency.
So when a photon gets absorbed by an atom, which is basically it running into the electron, making the electron get in a bigger orbit or whatever because it's got more energy temporarily, then what has happened to that little the Ton pair there? That they're stuck to the electron, or what are they doing before they get fired out?
They both came in at the same.
Does it wrap around the electron? I don't get this geometry.
They changed the shape of the electron, so they give it's like a tire tread on a tank. They give the length of the tread more tread. So they add a tread to the length. You know what I mean? So they make the tire tread. The tank tread gets narrower. So instead of a really tall tank tread, it gets narrower and narrower and narrower. So when the photon comes in, it gives it tank tread, and it gives tank tread in a direction.
Because you mean the electron is made of all these pairs.
So the electron
swarm, like the fish metaphor.
So think of
so it's got one more pair of fish or whatever.
Think of it as like a galaxy, right? The electron. And then think of it as it actually rolling on a surface. Okay, so when you actually do push 2 into it like a wheel, it'll actually cause it to roll. And so that's the movement of the electron, is the electron gains momentum because it absorbed the photon and absorbed the photon in one direction. Both of the photons that came in, right, both the tons were moving in the same direction, so they added momentum in that direction to the electron.
I do think it's getting more clear the way you put it, and I also see how some of these metaphors you've been using for a while, maybe where you were going with them. So that's an interesting system. I've got to go to bed. It's almost 2, and I got to work tomorrow, relatively ordinary time. But yeah, that's interesting. So I mean, there's definitely other things about, you know, how do all the details work out? But I see what you're saying with these pairs and why some particles are, in fact, the stream of BBs from one of those machine guns, or a ball of, you know, BB magnets that are clumped together, or, you know, there's schooling or whatever. Yeah, and to a certain degree, I see how a lot of this would end up being compatible mathematically. You know how two systems will like on the infinite, they'll converge to being able to do the same kind of math.
Well, I'm just saying it creates tremendous conservation. I'm just saying that's one of the great things about this, is that it really makes conservation obvious. So that's my, you know, thing. But
yeah, I don't see the objection to the particles, or Hythlodae's objection to fields, or any of these. To me, these are just words for phenomena. We're looking what it is. Shouldn't have a preconception exactly. I mean, to me, the main thing you have is how physical things behave in all these controlled conditions. And but you're trying to explain that stuff too, so I see where you're going with it. It would be fun to do some math. I mean, if you ever make it clear enough with the computer, it can be straightforward to play around, make graphs and stuff of the
I know
ideas.
It's already been done. I mean, Feynman diagrams are actually pretty good. I mean, they're actually, I mean, the momentum numbers come out.
I've been thinking of getting a tattoo for about 10 years of a Feynman diagram. I figure that's about the only thing I could think of that I would pretty much not mind having, no matter how old or saggy it got or whatever.
Well, I'm just saying that's pretty, when you get to it, the Feynman diagrams are pretty much you know what I'm saying? They're pretty much this rudimentary. I mean, something goes in, something comes out. The conservation is there. Yeah. And, you know, there's no bent space or any other kind of crap going on.
Well, and they're definitely just a device, but the cool thing about it is it's like a very succinct way of making a picture worth 1,000 words and whether there's anything like that. He wasn't saying something like that was going on in reality, but it's a way of visualizing a process. Then you can look at the picture and make all these calculations. And if you want to do all the differential and calculus math, you can actually get numbers out of them, all in something that when they try to write out the equations the old way, you have, all these pages of impossible stuff. So on the other hand, they're always, they're all approximations. Like a full Feynman diagram is supposed to have an infinite number of lines all over like a mess, but you only have to do this probable ones, right? If you get out to a certain level in a simple interaction.
Well, all I'm saying is that the time component in the momentum is pretty much my kinetic argument. So it's pretty much a description of kinetic interaction. That's all I'm saying. So it's very useful in the sense that you'll understand that, yes, the mass of the body that's getting hit by the other body matters. Its momentum in a direction matters. And yes, those calculations are incredibly complex because you have two moving you know what I'm saying? You have the internal moving parts. But I mean, it's always difficult to extrapolate what, you can't just do a simple fraction. You know what I mean? I mean, I like it to be that simple, but it's not a simple fraction because we know that everything is moving in a charged field. And so you have to know the whole field it's already in, in that charged field. It's like doing the gravity thing with 10 gravitational bodies. You know what I mean? It's almost impossible to do it exactly. You can only approximate it. Just to do it exactly, you'd have to account for every second of every change that moving closer change. Every time the Earth moved 1 inch, you changed the position of the sun, and now you got to move the sun, and now you got to move this, and now, it's impossible.
Well, yeah, in quantum mechanics, it's so impossible. With ordinary computers, they could be thousands or even million times faster, and they wouldn't be able to get very complex in terms of like simulating what, a cup of sugar and milk would do.
Right, but I just mean the exact numbers in a world.
But you don't need all that detail for a lot of things.
Well, exactly where stuff.
But if you have a dream of using math and Newtonian or quantum or any of these systems to figure out everything, it gets too complex too quick. Even though in principle that you could figure out some part of it becomes really important because you just figure out how to make a computer. You don't have to simulate a cup of milk. But anyway, okay, well. You should get, isn't it morning enough now? Does Heitzlede show up?
No, well, he's too retarded anyway. I can't really.
We gotta get him in here. This would be fun. We got 3 of us on this.
Yes, he had to take.
Oh, and Anna Kanavad.
Yeah, right. That would really make it fun.
Okay.
Well, what's a desire? I don't know. It's a magic desire.
That was fun watching them argue about that.
Well, I don't know. It's really complicated. Breaks determinism for sure. I
hope my questions helped clarify for some other people, but whatever, because I get it a little bit better what you're saying with the Flocka.
Yeah, well, look up the aspect. Look up the entanglement aspect experiment because I have an explanation for that. I can undo entanglement now.
I know. I'll look that up. It's you're saying entanglement
aspect is the guy who did the thought experiment of Einstein, where Einstein was trying to demonstrate that entanglement is unplausible, spooky, actually, and distant. And Alan Aspect supposedly did the experiment.
I see this guy.
I can explain why Aspect's experiment doesn't work.
Okay, I'll read up on it. I'll probably, if it's that famous, I probably heard the results or something.
Well, it's the only entanglement experiment there is, as far as I know. It's the one.
Oh, Jesus. Okay, I'll keep that in mind too. No, I think there's probably other ones, but I'll see what you mean. I'll look up what
I'm just saying they're all variations on his theme. They're just bigger ones. Okay, it's like an interferometer. Okay. He invented the interferometer of entanglement experiment.
Oh, okay, cool. Yeah, I'll look it up and see what you're talking about. Okay. Then I'll let you debunk it. Wait, so how often are you doing these? Just whenever, or?
Well, you can look on the channel. I do them every couple of days.
Well, I've seen a bunch of them, but I was too
every couple of, it comes out to like every couple of days. That's when I do them.
No, I've been watching some of them, but they're long enough. I didn't watch all of them so I've seen the beginnings. I wasn't sure if Heitzlede or someone else showed up towards the end or what. So
nobody usually.
I've just been too busy. So maybe it's getting more ordinary. I don't know.
I'm just saying I just making my arguments about different aspects of
No,
this.
I've been watching, but I'm
Somebody
just saying I
shows
haven't
up and
watched all
somebody
the
shows
hours.
up. If no one shows up, no one shows up. So it's
Right, you do it as a video thing.
I'll
That's
just do what I can do, and that's all I can do. I give people a chance. If they got an argument to make it. If they don't, they don't. So I'm giving them their chance to debunk me. So go.
I wonder if we should do as more of a theme. We then some of it is IRV. IRV is on the ballot up here in Maine to do IRV voting.
Well, I know, but without getting rid of the geographic thing, okay? As long as you're still voting in geographic districts, it doesn't do much.
Well, right, but the one is more likely to lead to the other than.
I'm not saying it's not a good thing. I'm just saying that it's a 10% solution. It's like putting solar panels on the roof, okay? It's just not the best place for them.
I'd run on a non-geographic, except for you have to allow there to be some geographic. There's no way people would give up all township.
Well, I'm just saying local can be local. I'm just saying that federal elections can't be reduced to
right or state
geography, because then you're just voting your state. You're not voting.
Fair enough. Then, yeah, that's what I've always thought too. Right, at the state level, don't have it be the state senator from Cumberland County. Have it be.
It always makes it just a Democrat Republican. It just creates a two-party system. So I'm just saying, if you want to break the two-party system, you got to get rid of geographic districts.
There is a little opening to do that in the next some number of years, from the fact that everybody's finally aware of gerrymandering and how you could sell it as breaking gerrymandering, because gerrymandering is made geographic ridiculous.
Well, I know, but it breaks pork. It breaks all of the local bullshit, and it makes people like Jack Kevorkian could be in Congress.
Well, I think
assholes. Okay,
you've been wanting this kind of thing for so long. It seems like, oh fuck it, people will never get it. But IRV, these things do come along. And I think there might be a time to get at least public awareness of the non-geographic.
I'm just saying the half solution is no solution. So I'm just saying it's like the right to die stuff. They think they solved the problem in Oregon. 70 people a year, are able to jump through the hoops.
No, but that's how you get
70.
the next step.
I'm just saying it's not a solution. 70 people a year is not a solution.
You got to keep fighting, right? That's why
it's not even close to it. But no, they're not going to fight because they think they solved the problem.
That's the whole thing about the anti-SJWs. They don't get it. Why aren't they happy yet? It's like, well, because that's not a solution. I'm sorry.
Well, I'm just saying I don't want the half answer to win, because the half answer makes people think they solved the problem. That's my point. My point.
I think it's case by case. Some half answers.
Don't accept the half measure, because then you're going to have to live with it for the rest of eternity. I'm just saying.
No, it does slow things down.
I'm just saying
it's better than no progress.
Well, no, but it isn't. Unions aren't better than constitutional rights. They're having individual unions fighting for rights isn't as good as having constitutional worker rights. We need constitutional. All workers need to be protected, not just Teamsters, not just the ones that have extortion power. So that's the big, huge flaw here. We've accepted
and it's slowed
and
down.
says, oh, well, there's unions, so it's okay. Well, it's
that's
not
why they corrupted away. That's why
not a good enough solution.
So the alternate is, let things build up to the point where it's so obvious there's real change.
Well, I'm just saying that
I'm just saying it's case by case what you want to do.
You can't let the good get in the way of the best.
Well, right, but getting IRV voting for the offices we have now is not a measure.
I know, but I'm just saying that people keep thinking they've solved the problem. San Francisco thinks they solved the problem. They didn't even come close to solving the problem. I'm telling you,
that's the whole anti-SJW thing as far as I'm concerned. Everybody wants to say, well, why aren't you happy? And it's like, well, some of us noticed the problem isn't totally solved yet just because it got better. It's like I'm a house slave now. That's not necessarily good enough. You're not free yet.
Well, I know. Anyway, I don't know if I'd make that comparison, because that's not exactly. Women have made a huge. They really are a lot better off. I'm saying that it's a 5% versus 100%. So
well, I'd love to get into that.
Instant runoff voting without the geographic freedom is a 5% solution. That's all I'm arguing.
I'll think about the relationship between those, because I feel like they're separate enough that either one of them would be good on its own and lead to the other, if anything.
Well, I'm just saying that if they don't, I don't think that the tendency is that it leads. That's all I'm saying. I'm saying that people get satisfied that they accomplished the task, and now their job is done. and that's the
I
wrong.
do think that it's an interesting thing because though I remain a feminist, I believe it's an international thing, and I do believe there's a lot of gender issues still in the United States, but we're at a point where we really should think of it as gender activism, gender rights, looking for gender-based diseases and stuff, because in that sense, it actually has gotten to the point where in our little bubble, you could say, well, let's mellow out about that, and the people that don't want to mellow out should fight for it in the world.
Feminism will never be died because it'll never be done because you can never undo the unfairnesses of nature, okay? You'll never undo the fact that it's a huge burden to have babies.
Well, these liberal colleges...
Having a baby is a huge burden. Having a period every month is a huge burden.
Some of the liberal arts colleges, are, you know, they're calling them gender studies departments and stuff. It includes feminism, LGBT.
I'm just saying that whatever these guys are afraid of, I'm saying...
Well, you know we agree on that, right?
There's nothing to be afraid of. I'm just saying that it's not like women are cutting our testicles off or something.
Yeah, no, we agree on that even in the current case. But I'm saying it is going in this case where there's a point at which the ongoing thing is gender issues because, for example, there's a medical side. Men and women can get new kinds of diseases and cancers as as things affect the different body types differently. So, you're always going to have these issues. You're probably going to have various kinds of bias, or you're going to have the sociology of girls and boys at different ages is going to be, drifting, and you might have a problem like boys suicide in Malaysia or something.
I know, but you're never going to make the two sexes the same, so it's just silly. Men are disposable. Men are vulnerable to all kinds of emotional issues because, they can't do their thumping on my chest thing and blah, 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 blah. I
do agree that. So you agree with that? Yeah, I think the disposable male is a real thing that the MRAs complain about. It is a real metaphor. I consider it as part of patriarchy, though, but it is a real thing. For sure.
Yeah, I mean, it's just a fact of nature. We're not made. Of course,
the disposable poor person is bigger.
We're not made to be civilized, okay? We're
built
civilized.
Right.
So yeah, being civilized is going to require some sacrifices. So yeah, so you give up a little. It's no big deal.
The thing is, the disposable poor person is about 1,000 times more of an important phenomena than the disposable male as an issue.
I'm just saying that the disposable honest person is what it comes down to now. Because no such thing as poor now. I mean, poor is you're poor if you have an honest job, because honest jobs don't pay.
That's a really interesting thing. It's the disposable honest person. I believe that, like the whole idea that honesty, none of us are truly honest, but if you even have one honest act, you start to see there is this...
The society places...
You get taken advantage of for being honest. One way to look at it is the disposable honest person, because everybody appreciates the honesty, but it's disposable of them, like a candy bar. That's why they do that shit and look so thankless. You'd think, be nice, I'll do more nice things. No, they just dispose of it so often.
They'll just eat it and you're dead. So
yeah, even though it's possible to like plant half of it or whatever, because of the disposable thing, it is. It's like the disposable whore, the disposable poor person, disposable man. These disposable ideas is almost all of the slavery. It's all thinking other people or living creatures are disposable.
That's capitalism, frankly.
That's a pretty good way, because I like to put like activism, generalize it in terms of the effects of war and stuff, but really even war, it's this other way. No, it's about on an individual, thinking an individual, and then one at a time, and then thousands of them together, all disposable.
I know. Well, you have this pipe,
including your own people.
you have
really,
this
right? To go to war, you have to think your own people are disposable, not just the motherfuckers you're going to kill.
Well, I'm just saying that everything's run on return on interest, and I'm just saying that there is no value outside of that. So if there's no return, there's no investment. So there's never going to be a future with robots that take care of people. There'll be just robots that take care of the rich.
No.
And, well, I'm just saying that's the practical reality. Because the regular humans have no value.
Anonymous will install different software.
Yeah, right. Okay. So,
see you later.
Yeah, all right. Take care. Or not. So anyway. Well, at least it wasn't terrible. I didn't have to go totally insane. So, but you hear the concession. Oh, yeah, that's plausible. Yeah, I get that. Yeah, oh, yeah. And, you know, next time it'll be like that conversation never took place. You won't remember a thing about it. It'll just, no, that never happened. I never said I got that. I could see how that could maybe possibly work. No. So what's this blank thing in my room? It's a gray icon just sitting there. Ian. Yes. Wonder who that is. There's a couple of Ians around. It certainly couldn't be Ian Crossland. I guess he's crazy. But hello, Deirdre. Yeah, I know. It'll have to do. So hot as hell in here still. 88.5 degrees in my house. It's a little bit outrageous. Especially for 2 o'clock in the morning. I mean, come on. Yeah. I definitely have to put a fan in the window or something. That's just too hot. Too hot for arguing. And such. So I think I did, but I think, it's just everything. I can, I mean, anything Piro brings up, I can, yeah. Some guy did post something. I did want to mention that, unfortunately I had to delete some other crap somebody posted on the message board on the website. And when I was deleting the other crap, I ended up deleting his comment, but he was talking about some kind of zontons or some kind of other, they found some new photons that, wear Mexican sombreros and go Olay or something. I don't know. I'm quite skeptical. Photons have been around a long time. If there was some new special little fancy photons, I'm sure we would have heard about them by now. So I have my doubts. And certainly have my doubts that photons have any other property besides polarization. And they keep talking about spin, and then spin just ends up being polarization. So it just seems like they're playing a game there. Spin up and spin down on photons. I don't think so. It's just going to be manifested as polarization. So I think that's bogus. Very bogus. Mostly bogus. So, but I do have to get some physicists in this room somehow. Somehow I have to maneuver them. I have to trick them. Some sort of nerd candy or something. Like free pocket protectors or something. I have to figure out some way to, I could have like a whole wardrobe kit or something, a bunch of like little belts that are like a 1/4 inch thick, and pants that have really long crotches, so they can pull them way up to like their neck. Can you speculate on how the quantons form into electrons? Well, that's sort of like speculating how suns form into galaxies. I mean, obviously not the same thing, but it's the gravity, stupid, right? And the gravity gets turned into magnetism on the level of the formation of electrons, for example. So it's just the pressure argument. There's no other way to say it. So if I made a field, if the screen you were looking at, if you thought about each one of the little pixels as being an arrow going in a random direction, and that the screen overall has the same number of arrows going in every direction, you could sort of think that whatever spot you pick, you could just pick any one of the pixels and just say, I'm going to be this spot. And then that spot, right there, that spot, from the rest of the world, you would see that there's arrows pointing right at you. You would look out and you could see them pointed right at you. They're going to come right at you. And that's basically gravity. So gravity is the fact that you'll have a whole bunch of arrows that are pointing right at you. They're coming right for you. And that's the pressure. And as soon as you have a pressure field, then you just put two things next to each other, and you can sort of see how the pressure field will keep them connected. It'll end up creating low pressure between them because it's all straight lines, right? None of the stuff can go crooked. So if I put two things next to each other in straight line force, there's no going around the corner, right? There's no, woo, I'll fill this space in here. So this space becomes a real shadow, a real low pressure, so to speak. And so that's just the photons, the tons, the gravitons end up becoming a photon because they end up being like the arms on the galaxy. They're counterbalancing mass. And so they have an attraction from the external pressure and the shadow. They keep casting a shadow on each other that bonds them together. But that would be what electrons are, is like a hurricane of photons, quantons. You know, they will be photons when they're released because they'll be released at a frequency. But they're quantons while they're in the electron, so to speak. But in a sense, they're just positions, which makes this even more complicated. I mean, I hate to, you know, it's like if you really want to explain it, it gets a little more complicated. It's all the straight line vectors. You have to keep thinking about them as just being straight lines, and the straight lines from each direction end up making a circle. If you think about like the top of a wheel, and just think about, well, think about any round thing, and just think about straight line here, 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 straight line here. So that's really what's happening, is all the way around the wheel is all just straight lines, things. And so it's just an illusion of the wheel, sort of, because it's just about the polarization that defines the form of the electron. The electron is just a collection of these things, these lines, but all polarized the same way. So at each location, at each little spot of the wheel, the polarization is all the same. And so when the line comes through, the polarization stays. So if it has the right polarization, it stays. If it has the wrong polarization, it goes through. So that's how the filter of the electron is maintained. Is the electron will only absorb the photons if they're coming at a frequency and they have the same polarization. And it's the same polarization as the electron. So they all have to be in the same plane. So it's like hitting it's like if you shoot a gun at a galaxy face this way, you know, spinning flat this way, you know, this way, it's really easy to miss the galaxy, right? Just to go right through something. But if you shoot at it this way, you're more likely to hit something. So it's that kind of argument. Not the same argument, but it's like that. Electrons have a geometry, and so do the photons. And when their geometry matches is when the electron will grab them. And when the geometry doesn't match, that's when it just goes right through. But yeah, it's hard to, it's really a simple mechanism, but there's, you know, the complexity is in the density of it. And so that's where it's just so hard to say, well, imagine a billion little specks, and then imagine, you know, it's really can't do that. So, and then when you break it down to more manageable numbers, you sort of start cheating the reality, because it isn't just 4 things going this way, 4 things going that way, and 4 things, you know, and those metaphors stop. You know, there's a point where they're not going to be completely applicable to the reality. They're still useful. I mean, I think the school of fish is useful. I think the dancing analogy is useful, but it's obviously not explicitly accurate. To answer your question. Yeah, kind of long answers. It's sort of what you're stuck with, though. I mean, see, the nature of physics is just so, they've got it so wrong that every time you answer a question, you have to explain, well, look, just ignore what they say because they don't understand what a photon is. It's like Piro. It didn't even occur to him to think about frequency as being the period between something. He's thinking of frequency being the thing itself, like it has a frequency, like it possesses it. You know, like the moon, and so you could go, moon, and it has a frequency. It's one moon. How could it have a frequency? That, you know, where that's like, that's how unintuitive it is to me. Because see, you know, back in grammar school when I was first introduced to this idea of photons and electrons and all this kind of stuff, I couldn't imagine photons any other way but then things moving at a frequency. It just seems so obvious to me. I couldn't imagine some sort of wavy thing flying anywhere. It had to be at a frequency. I mean, that was, to me, a frequency was like bullets. They're at a frequency, you know, depending on how, you know, fast the gun can shoot. But the bullets themselves don't have a frequency. The frequency is a byproduct of their circumstantial arrangement to each other. But the individual bullets don't know anything about it. They don't know, you know, like a photon doesn't know it's a photon. It thinks it's a graviton, probably. It's just saying, I'm a graviton. But no, you're a photon because there's a guy coming right at the exact number of seconds right behind you. And that makes you a photon now. So you thought you were a graviton, but you're not. Yeah. For our viewers, boy, it's pretty pitiful. You really do have to have door prizes or something. Yeah, or something. I do have to stir up some more interest. So the quantons in the electrons keep being knocked back by the pressure field into its space. Well, knocked back is a tricky word. I'm just saying that it's a similar mechanism to the gravity you can understand holding a galaxy together, right? So if I told you that a galaxy had very little mass in the center, and that really the arms were gravitationally attracting each other, right? The balance of the half the pie on each side of the wheel kind of thing. It was the gravity of the spiral arms that are pulling on the other spiral arm opposite it. You could sort of get what I'm talking about. Well, I'm saying that what's holding an electron together is the same kind of idea, except it's on a much finer level. It's the resolution is depicts the things are actual things you can see. You know what I mean? It's not gravity anymore. It's like seeing if I took away gravity and I replaced it with bowling balls, and the bowling balls actually flew through the galaxy, and you could actually see the bowling balls hitting things, and then you could see them shadowing, you know, where the bowling balls get shadowed, and you'd see where things don't get hit with bowling balls, and therefore there's more bowling balls on one side than there are the other side, so the thing moves because there's more bowling balls on one side than there is the other side. You know, I can make it understandable. I'm just saying, but obviously on the resolution, the size resolution of the atom, it's not, bowling balls isn't a very good analogy because their impacts are bowling ball on bowling ball. It's never bowling ball against galaxy. It's bowling ball against bowling ball in the world they exist in. And so that's a different dynamic, obviously. It results in the same effect. It's just that the way the effect plays out is different, if I can say it that way. It's the kinetic rules that are governing the subatomic interactions, and at the galactic interactions, it's hard to see the kinetics because it's all about mass and momentum. But the mass and the momentum is made up of the bits and the kinetic interactions. I think that was a good enough explanation. You really have to think about it in terms of fields, because it does make it easier to conceptualize everything. Because there's just such a strict conservation rule. So, anytime something does something, the field outside of it gained the opposite thing. So if some little piece of something goes this way, the field around it has to be going that way. There's an automatic, and then if it's going that way more than this little bit went this way, then the field wider than it has to be, generally speaking, going that way. So, when you think about it as fields local to the bigger you get, the conservation still has to exist. So if there's anything happening in a local area that's imbalanced, the exact opposite of that imbalance has to be in some external field to end up with balance in the total field. So in the biggest field of the whole universe, there would be perfect balance. And it's only in sections that you can have, in localities, that you can have the imbalance. But they all have to be transmitted through a less local field, a wider field. So the force always has to be equalized in the total field. And you can really see that with electricity. It's very interesting. I mean, they say there's no, they think there's monopoles in electricity, but there really isn't. Because there's always the opposite charge. So if the electron has a charge, there's something else that has the opposite charge, in the sense that if you have spin going one way, there's something else that has to be spinning the opposite way. So it already exists in the wider field. It just depends on how far away it has gone, whether it still has an effect on you or not. So it's like a rocket exhaust. Clearly in space, the exhaust seems to be gone, okay, and your momentum is gone. It doesn't seem like there's any place where those two things are going to neutralize, in terms of the field dynamics. So there are circumstances where, it seems pretty likely that your exhaust isn't going to jump back in front of you at some point. But in a lot of circumstances, your exhaust never gets out of the local field. The local field keeps bringing it back, keeps swirling in some direction. So you fart, and then the fart travels through the swirl of the bigger field, and then eventually you'll fly right into your own fart. Yeah, interesting. Another good metaphor. So yeah, that's the trick of fields. But yeah, so there's no really electric monopoles in a sense, because the electron is always, there's no such thing as a neutral place you can put an electron, unless it's a highly charged circumstance where you surround it by a bunch of other electrons. So you can only trap it in a more negative field. You can never have a free electron, because there's always going to be a positive field it's heading for. So it's always, the two sides of the magnets exist, whether you want to, it's not a monopole. The electron has its positive counterpart in the protons that it seeks, that it's attracted, in the field that it's end up attracted to, in the less negative field that exists. The less negative field is evidence of the it not being a monopole. So you can never take an electron and just place it in space, and it just would say, I'm fine right where I am. It won't do that. there's always going to be an imbalance in the field relative to an electron. Let's see. So, okay, that's the old question. Think when I grow up, I want to be like you, Mindy. Yeah, I saw your video. You looked very. It's like either your vehicle is very big or you're very small. It is kind of funny how your camera kind of really distorts. I mean, I know it's just probably it's just a weird visual effect when you put a camera on a dashboard, but it was kind of funny. So your whatever sympathy video and whatnot. Yeah, you just have to take some, heroin. Yeah, get over it. Yeah, there's no real getting over anything. Every day is just a struggle. It's always something. It's like I got, it's too hot today, so I got, whenever the temperature goes too high or too low, I end up with this jaw pain. So it's like all day, just saying, not terrible, but just this dull kind of ache. It just like, it really just takes a charm out of living. 4'11" is kind of small, huge. It was funny. Yeah, I was just thinking you're driving trucks, and I just, yes, we have to get you a job driving trucks. Because I just love the idea of a 4'11" girl in her Mack truck. It's just too perfect. Little booster seat. Yeah. Or even like a bus driver, with like 24 gears on the, on the bus. I don't even know if they make buses like that anymore. They're probably all automatics now. Everything's in, taking all the charm out of driving. Yeah, so I like that you still had a stick shift in your car. Oh, well, that's great. So I'm glad you got a job trucking. Yeah. Yay. Probably like delivering something stupid, but what else? I guess you can't have everything. But let me know if you ever get like a cigarette truck or something. Yeah, I'll have to plan some kind of elaborate scheme. Martians will steal the truck or something. We'll have evidence of the Martians and something. Blah 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 blah. Have to come up with some kind of scheme. A plan that cannot possibly fail. Yeah, I don't think I could. I like driving to a point, but yeah, there's only a certain amount of driving and I'm done. Yeah. Now I can't tolerate cars at all, but when I found them tolerable, they still weren't tolerable. Was this when I was a kid? My parents used to travel all the time, so we were always in a car going somewhere. I really didn't like, I got a little bit car sick. I was really just not very comfortable. So I think it really fucked up my brain. But anyway, that's not physics. Well, I suppose everything's physics. I suppose. So, what else? I don't know if I have any other physics for now. So my brain's a little tired. And I probably should go to bed and all that kind of crap. But it's nice pink moon and D in the same room. Very nice. And what else? I think there's something else. Yeah, I think that's enough. Yeah, I really, I got so many things I have to do. I'm fucking around doing this. I keep evading. It's like today. Today I really should. Well, it was really hot today though, so I sort of have an excuse. So I just did gardening. It's like it's not a paying job there, Gary. You really got to get other shit done. But it's just, day's a challenge and whatnot. So that's it. Okay. There's something new. What is it? Yeah, I don't want to interrupt. It's interesting. Wish I could understand more. Love physics. Yes. Yeah, what is? There's definitely a learning curve. And then once you know it, it's it's like everything. When you know it, then you start talking like other people know what the fuck you're talking about. You just, oh wait a minute, yeah, they don't know what I'm talking about. So I know that I start to get more distant from regular person conversation. But I think I'm to a point where I have the vernacular or the conceptual conversation to actually have a conversation with a real physicist. So I think I know enough of their jargon to get the job done and still be balanced enough where I could explain it to the regular people. I think that's why I come up with metaphors that are, the dancing metaphor, the fish metaphor, because they're just such, bowling ball metaphor. It just makes it more easier for people to understand. Yeah, why are there so many tree species in the rainforest, like 100 different kinds per acre compared to 10 acres in New Jersey? Well, I guess it's because of the, let's see, what's this, the most obvious answer, I suppose, is that it's more primal. So you start reducing the number of species the further north you go from the equator, let's say. So the colder it gets, the more intolerant certain species will be to that classifier. And so it gets to be, the trees in the rainforest are dependent on the biosphere of the rainforest, so they need lots of fertilizers, they need lots of living things to die so they can feed on them and their roots, blah, blah, blah. You can go through all those kind of systems, those kinds of explanations, and then it also has to do with how much water there is and moisture and blah, blah, blah. And so the further north you go, the less and less, and so there's less and less diversity. And then when you get when you go far enough north, it's just pine trees. You know what I mean? You don't get any oak trees anymore. You don't get any of this. You don't get any of that. It's just pine trees. So I think it's pretty much probably has mostly to do with the fact that even plants need a biosphere to feed on. And the less biosphere there is to feed on, the less plant diversity you'll have. So I guess that's the easiest argument. That most living things find it a lot easier to live where it's warm than where it's cold. And metabolism-wise and everything, it just works better to be in a warm environment than a cold environment. And especially when you think that most things are cold-blooded, so to speak. They need the sun to heat them, or they need an environment that's warm to have a metabolism. They don't have one without it. And it's only the mammals that really made the transition. So you don't even have any big animals except for mammals, up north. No snakes or anything. You don't find any Alaska snakes, right? Well, yeah, Alaska you will. I mean, it depends on the part of Alaska. I mean, there's no such thing as like a polar snake, So, polar python. So that would be the simple answer. I mean, off the top of my head, explanation. Let's see. I heard that it has to do. Well, if you already heard something, why the hell were you asking me? I heard that it has to do with the amount of available energy. Well, that's what I just basically said. Right. Exactly what I said, actually. How many can it be? Well, I'm just saying the niches are, you know, I don't know why you would think it would become a monopoly, because monopolies don't work, right? Let's say you become very successful and you take over. If you do it as a predator, you'll kill everything. You're right. If you do it as like a prey animal, then you'll be food for everything, right? I mean, if you become abundant, it's like funguses are. Always use this as an example because it's this thing that theoretically they could be growing on everything. They should be growing everywhere because they can grow on almost nothing, right? I mean, they need so little nutrient, and but they don't. And the question is, well, why aren't they covering every surface? Why isn't every surface just covered with bizarre looking funguses? Well, because that's their strategy. Their strategy is don't look like food. And if you're everywhere, something will start eating you. And so if you don't want to be food, don't be too abundant. So even though there's millions of varieties of fungus, and even though they're highly successful, it's like certain ones like that. There's actually a fungus that looks like a basketball. Amazing looking thing. It's the size of a basketball. And I see one maybe once every 3 years. I'll find one, and that's it. Once every 3 years, it's a fucking mushroom shaped like a basketball. Huge. But yeah, once every 3 years. So it's something that could grow every year. It could grow everywhere every year, but it doesn't because it doesn't want to be food. And you know, when you see them, you'll see that deers have taken a bite out of them. So they are almost becoming food. You know, even though I will find one once every 3 years, they're still close enough to food for something to take a bite out of you. So imagine if you were successful, yeah, then they'd learn to eat you. And then you'd be doomed, because then they'd just eat you till you're all dead. So that's the explanation for diversity, is that it's a monopoly doesn't work. You'll fail in the long run. So anything that monopolizes fails. So the tendency is not to do that. But there's all kinds of cycles. I mean, there's all kinds of times when certain species will be dominant, and then that species will get a virus and they'll all die off, and then something else will be dominant for a while, and blah blah blah. So who's winning at any one moment is always changing. The warmer the environment, the more niches there are. I mean, look, there's plants growing that only grow 100 feet high in the water collected in the cracks in the trees. So there's flowers growing, you know, in the branches of trees 100 feet in the air. So, you know, I mean, just so many niches. But, you know, the whole point of a niche is the niche has to be far enough away from something that might eat you. But fungus has structural limitations. Trees can grow taller and are more durable. Well, I'm sorry. If you think funguses aren't the most durable thing on earth, then I think you've got something to learn. Fungus is a hell of a lot more durable than a tree. Trees can be infected by millions of parasitic bugs, woodpeckers, all kinds of things can destroy a tree that quickly. But they don't, because if you do that, you destroy your food supply. That's my whole point, is that evolution has been cooked over millions of years in the short term and billions of years in the long term. But I mean, it's millions of years, and over those time, the one lesson that's always learned is you can't soil the environment. You can't shit in your drinking water. So there's certain rules you got to obey, and so you won't. Organisms just won't exist that have any attributes that don't include this some mechanism, like dying, right? Everything dies, right? Well, why does everything die? Why doesn't everything ever not die? Well, because not dying in the past has always meant you're going to overpopulate. So dying was a necessity. And it's only the most bizarre organisms that can live 10,000 years or something, some trees. But obviously it's because they don't reproduce, any kind of rate. So they've broken their reproduction to accommodate their longevity. But the price of that is like, the redwoods in California. I mean, theoretically, they could be wiped out by a big enough forest fire. Well, a lot of them, actually, their seeds will survive a pretty intense fire. But anyway. Why do most species die out after about 2 million years? Well, that's another question. I guess it gets into the genetics argument and all the sloppy code. And it's not like you die out. It's that the better version wipes you out, right? I mean, nothing dies out. It's something better than it exploits the environment. So it's not really that they just die out. They get kicked out. I mean, Neanderthal probably got kicked out by, the modern humans. Probably did a lot of slaughtering and genocidal attacking and whatnotting and helped them over the cliff. Even though they were bigger, they were dumber. And I think the little shits just kicked them out. So they didn't die out, they were slaughtered out, eradicated. But I mean, some species, come on, there's been dragonflies for 300 million years. There's been all kinds of insects that have been, they're almost pretty much identical to what they were 300 million years ago. Amazingly similar. So no evolution required. No dying out. They're like a perfect machine. And the ones that are funny, like dragonflies, you wouldn't even think that would be the description of a perfect machine, right? Because it's so bizarre in terms of its metamorphosis, from a little sea bug, living in a stream, eating fish and shit, to being, this delicate flying insect that eats mosquitoes. It's just amazing. I suppose the world doesn't stay stable climatically more than a few million years at a time also. Well, I suppose that's part of it. We don't get to see all the evolution in dinosaurs and all that stuff, but they obviously stayed the same for a long time too. So, there is a tendency to, once you make a machine that's a really good machine, that machine is going to stay around because it's durable. It's survived the test of time, as they say. And it's only going to be a catastrophic failure that'll kill it. Right. So, and such. And so forth and whatnot. Stuff gets very eccentric, it becomes so dependent on its environment. It's like the dart frog, all kinds of other stuff, they're very eccentric. They can only live in certain climates and certain exact conditions because their whole biology has gotten caught up in, it can only lay its eggs on a certain kind of plant leaf. And, all those kind of dependencies can make you very vulnerable to extinction because you're just become too dependent. It's like almost fish that, like those fish that clean sharks and do different things, fish, then they start becoming dependent on it. And if they don't have the thing they're dependent dies, then they end up dying because they become dependent on the service. They become dependent on the food, it's like whales. Some whales will eat one thing. If that thing dies, they're done. Yeah, well, there are slight variations, but they're punctuated equilibrium, right? So there are slight variations, but usually there are a pile of them happening over thousands of years. So let's say you have some inbreeding and, you have an isolated population. and yeah, you get the ability to fly, or you get, or you gain twice as size, or something like that. Yeah, and then you come back to your origins, like you could see that human beings went all the way around, to get to North America. They had to go all the way around Europe and all the way around, and they didn't face their ancestors until the Europeans came over. But I'm just saying is that you could imagine that there could have been possible that the North Americans, instead of being generally smaller, were bigger. And, so the whole, could have been a different dynamic, or they could have had, they acquired, I mean, there was only 7 females, responsible for all the North American Indians. Well, all the American Indians, they say, which is, there's only 7 females that made it across the land bridge. So it's a very small gene pool. So all kinds of punctuated equilibrium, all kinds of punctuated evolution could have taken place. Yeah, I don't know. The equator is a hard place to do any real science because, it eats up everything. So, you don't get very good fossils. You don't get a lot of, so it's hard to say, I think, what exactly has been going on in those parts of the world, because everything's just chewed up by it. But yeah, who knows? I mean, maybe it's more stable. I don't know. I saw, obviously, the older, I'm just saying it's the older environments, the original conditions. Warm and steamy is the original condition. So I'm just saying you obviously have the more artifactal kind of bugs and things will exist in the system more like the original conditions. Oh, Abba, you've just gotten so retarded. Maybe you could weather limits in psychology. What can be created? Maybe cold weather limits the physiology of what can be created. Well, I'm just saying it's obviously cold just means less active. That's, bottom line, more energy required. Cold climates, predators, more likely. And I guess you could call the, well, I mean, I don't know what I guess there's always the Brontosaurus triad or Tyrannosaurus circumstance or whatever, the plant eater and then the animal eater. So it's kind of an axiom that complex life thrives more in warm environments. Right, well, it's just energy. So entropy argument, or whatever you want to call it, in a closed system. Yeah, more stuff moving means more stuff moving. Yeah, so it's a simple way to put it. More energy in, more energy walking about. Since it's all E equals mc squared, I mean, all the matter is made out of energy. So more energy, more matter, kind of. Well, more movement of the matter anyway. So anyway, I'm tired and it is time to go. So, and this is, I mean, it's draft science stuff, but it is a little bit off the physics subject. Yeah, I don't think complexity is necessary, just the way it turns out. So, I mean, theoretically, I suppose there could have been something that really dominated and just wiped everything else out. It's almost like mammals as a kind of thing, and right, mammals kind of took over, and it probably put a lot of pressure on birds and other organisms that could have had a brighter future. I mean, theoretically, I guess it was, humans might have killed all the big walking birds. you know. So I'm just saying that there could have been a completely different world. I mean, the dinosaurs might still be ruling the earth in the form of giant walking birds or something like that. But it just didn't turn out that. Nothing took over here. So, I mean, but if you ran evolution a few million times over and over, it would be interesting to see what kind of differences, what kind of parallels there are outside of these influences, because mammals really just changed. That was like a game changer, the invention of the mammal. So, and it'd be a very different world without mammals. It'd be interesting to try to imagine what would fill the void left by the absence of the mammals. Yeah, well, it's too metaphorical or something. I don't know if we simplified anything. But anyway, Oakley Doke and such and so forth and whatnot. So, till next time, and thank you very much and so forth. All right.